Hello class, this is David Mulugeta. How we doing? I'm doing great. We are with Business Management 7250, Data Management for Analytics Professional. Today we'll have lecture 2, part 1, and the focus will be data and data mining. So this particular lecture is slated for Friday, October 16, 2020. So first, let's take care of some business on homework and reading. We will have our homework get ready submitted on the Friday, and the answers should be in the following Friday, like was explained earlier in lecture 1. And the reading assignments are given here. There are 2 papers that are really very interesting to know more about data and contemporary concepts. And also regarding Python, there is also reference material indicated, which is the second textbook. All of the information, of course, is available on the syllabus as well. Today we'll be covering data and data mining. These are the most important concepts in analytics. So at a higher level, there are 5 pointers that we will touch base. The first is, what is data and data mining? Why? Second is, what are the data types available? Third, the 4 V's of data, and this include volume, velocity, variety, and veracity. These are very important concepts as well. And the third, we'll talk about data measurements. Whenever you are doing any kind of analysis, any kind of machine learning, predictive modeling, always about, okay, what kind of data I should use and in what way should I really slice and dice it. So you need to know whether this particular data is going to be measured or not, this way or the other way. And finally, we will touch base data distribution, and this will cover the most popular 4 or 5 data distributions that we encounter on a regular basis whenever we are doing data analysis. So these are the 5 topics that we'll be covering in today's lecture. So why is data? In a very simplified form and approach, it is a tool to understand the world better. Using data, we'll be able to do informed decisions on various facets of life, on business, on customers, on products, on prices, on supply chain, on inventories, and so on. Data is very critical. It's central to many of the decisions that we are making, not only in business, but also in other facets of life. We also measure the effectiveness of a specific strategy, and through data we'll be able to really see the light, right? And data also is something that empowers us to tell a story, to really describe the events that are unfolding. And whenever we have data, we are really backing up our justifications, our arguments, and we really curtail any kind of guessing game. And it's not only that, but also using data we'll be able to really just like track performances of any kind of project. And this includes benchmarks, baselines, trajectories, goals, and so on. And of course, data is a component of the scientific method. I don't want to go through the detail, but whenever you are doing any kind of research, analytics, projects, data is central. So data is critical. Let's just proceed and see what are the components of data mining. So this is a high-level summary of the first reference material. And from there, it really just highlights data mining steps, what data mining is all about, and so on. So whenever we're talking about data mining, it is within the context of the textbook is talking about like predictive modeling as well. So quite many of the concepts that we'll be covering in subsequent time segment of this class are also indicated in here, but it is nice to appreciate what is the data mining as a process involves. Basically classification, prediction, and association roles. And within each one of them, there's so many methods that we can cover if we have the time. So data mining consists of these three major steps. Of course, there is also a bunch of other things that need to be done, including data messaging, data aggregation, reduction, exploration, visualization. And of course, we also need to really know lots of steps, including defining the data element, getting the data, exploring, cleaning, reducing, aggregation, choosing the right kind of model. We'll be covering all these concepts in the subsequent chapters or lectures that we will have in the coming 5, 6, 7 weeks. But this is just like, okay, what is data mining? Because this lecture is all about data and data mining. So I'm not going to focus on each of these steps, not really on data mining piece, but the fundamental one, the data. What is data? And what do we should know about data? That is my really major emphasis in this particular lecture. Data plays an important role in analytics. This is obvious. This is just like a component of the discussion that we have in the preceding 2 slides. So first thing, whenever you do any kind of analytics, you ask the right kind of question. What problem am I going to be solving? What is the guiding torch of my project, right? And then formulate the hypothesis, gather information, identify dependencies, get alignment from your business team for upper management or anybody who would be touched by this project, right? And then establish methods, identify tools, acquire data, and customer targets. Then you process the data, you explore the data, you massage the data. Then you analyze the data, right? You collect the data, small. Always, whenever you analyze data, always start from small and expand your analysis to the big one. That will save you quite lots of time and wastage of effort. You will be learning from small data and implement that learning and apply it into big data. And this kind of analysis is very iterative. Oftentimes, most analysis, it's not just like you do it once and you are done. You do it, and if you are making certain mistakes, you go back and redo it again. And eventually what you're going to be doing is generate information, share insights, and so on. So this is at the higher level what is analytics is doing. So in this whole process, data related tasks, and these are really numerous. We'll be talking about each of the tasks later in subsequent lectures, but data related tasks, data pooling, data storage, data messaging, data characterization, data definition, and all those things account, whether you believe it or not, it's 80%, sometimes much more than 80% of the work is all about data. Whatever kind of machine learning, whatever kind of predictive modeling you are doing, the bulk of your work will always focus on data. So that's why it's very critical, it's very crucial to know about data and to really, really be able to play with it. And at the end of the day, it's all about getting information from the data. So data, what it is, just like we have already seen what it can do. So in its own, data is a raw, unorganized fact about entity. Entity could be whatever, could be customers, could be products, could be about any kinds of processes that is in place, about an event, a history, whatever. So it is raw and unorganized fact. So it could be numbers, characters, symbols, strings, sounds, observation, and so on. These are all data. By itself, data is useless, meaningless. It has to be interpreted. It has to be processed. It has to be organized and analyzed and summarized by human or machines to make it meaningful. So data, as we know very well, has got different kinds of formats. By itself is useless. It has to go through this processing, cleaning, aggregation, modeling, and then data brings us information. And that's why we are so interested in understanding data and also the process it would take to really get the information that we need. And this information, of course, must be actionable and must be dependable, and it should really summarize or capture the ideas embedded in the data. So once we know what data is and what it can do, then we ask this simple question: what are the data types that we deal on a daily basis, on a regular basis, and what do we mean by data types? So basically there are two kinds of data. Data can be classified into structured and unstructured data. The structured data are the classic examples, the kinds that we are very familiar with. These have got columns and rows. It is like a specific table, or what they call it in Python, data frame. A specific table has got columns, and these columns sometimes called variables, and rows. Rows sometimes called observations. So this kind of structured data easy to search and always reside in some sort of data warehouse, like relational databases, which we will be covering later on. And most classic analytic workers are leveraging structured data. And when you are going to the flip side of the coin is the unstructured data. As the name implies, it doesn't have any columns and rows. It's very difficult to search. It's oftentimes put in applications or what we call data lakes, and oftentimes the unstructured data is much bigger than structured data. It is a new paradigm, and this includes lots of this social media information, images, videos, audio, text, streaming data, web pages, and all these are unstructured data. And there are also in betweens what we call them semi-structured. Suppose you might have certain kinds of picture. In this picture embedded are various kinds of information about the picture, about its address, labels, tags, and so on. So that kind of data, you can say it is semi-structured. But basically data can be broadly classified into structured and unstructured, and the features are indicated in here. So the same concept is shown in here, but the one I would like to highlight is that the estimated amount of data that we have at this point of time, about 20% is structured data and 80% is unstructured data. And this really make you think that, wow, we are really flooded with huge amount of unstructured data. And the surprising fact about this unstructured data, we are only using them, leveraging them, only 2% of this data. So that data is residing somewhere, looking for people like you to come and really work on this one and extract the information that we dearly need. And all of the characteristics that we have already covered are shown here on structured and unstructured data. Basically can be displayed in rows, columns, numbers, days, strings, require less storage. On the opposite side, require more storage. It's not gonna be displayed easy, and the storage different. The storage, the processing, and the analysis are also different. So let's just talk about structured data, the features. Any data that resides in a fixed field within a record or file is structured data. All data contained in relational databases, like various kinds of servers, there's several kinds of relational databases that host these kinds of data, and most companies are leveraging this one here. You capture point of sales data, you capture data about sales activity, markets, about promotion. All of them are residing in some sort of relational database. When you are stepping in a specific organization, company, firm, it's not uncommon to have thousands of tables. Of course, all of them, you cannot have access to all of them, and oftentimes, most of the time actually, the ones that you need for typical work don't exceed more than I would say about 50, maybe sometimes even 20, depends upon the kind of work that you are doing. So there are quite lots of tables in some sort of relational databases, but in reality, you would probably use a few dozens of them. And this kind of data are just like what you see here. There is this data, invoice data, milk data. Milk data is the one that we will be working on. It is a fake data that I have created, and we'll be using it in our Python introduction and subsequent works. And what it has there is it has got invoice, date, unit, price, promotion, and so on. So this is just like a typical structured data that we encounter in any form or condition. The structured data sources, they come from transaction data, and these are just from sales, from scanners, from shoppers data. All the stores are online. It can also come from generated by users or farmers. It's not uncommon for users to put their profile in LinkedIn and Facebook, and that's the kind of data that's being generated by the firms. You can also have some kind of experimental data. Lots of experiments or studies are underway by any university or any kind of business entities, and whenever you do any kind of experiment, what do? You collect data, analyze, interpret, and get this information out of it. Data also can come from the compiled, and this is really quite common, especially when you are talking about credit card score, demography, and all that's collected by specific groups, and the kind of data is used by wide consumers. So that is what you typically call them by compiled data. So structured data comes from different sources, and the inherent feature of structured data is the one that we have already discussed. It is the kind that we are very accustomed and most analytic people are comfortable to work with. We'll talk about when we are going to text analytics, how difficult or unpopular it used to be in the past, but it is getting momentum, and quite lots of people are embracing it at this point of time. So structured data, let's talk about transaction data. I would like to make sure that you really understand what transaction data is. It is nothing but when you are going to shop in Walmart, in Target, or any place, this receipts that you are receiving as a point of sale, as the just like the when you are paying for the goods that you are purchasing, the receipts that you are getting is called transaction data. What does that? It has got itemized records between the buyer and seller, information recorded on a receipt at the checkout counter, and this includes customer, store. Like if you look at your receipt, I have actually the next slide will show us. You have customer, store, date specific, bunch of other information as well, and that particular information is all what is needed for most analysis in any organization. So the moment you are stepping to work for any firm, the first thing that you must ask is, where is the transaction data? That is the most granular, the most important, and oftentimes called the mother of all tables. So whenever you have got this transaction table, it joins itself with many other tables, price tables, promotion tables, service tables, vendor tables. All of them, they come and link, and depending upon your desire or goal, you can analyze and get the information that you need. So transaction data is very critical and you must be familiar with it. So what does this transaction data has? It has got date. Of course, transaction data is date specific, happens in a specific day, right? There is a store number where it is being sold. If it is online, they also have some sort of stamp to really identify that particular location or your outlet or your IP address and so on. Customer ID, sometimes they identify the customer by the last digit of the credit card. The product, the list of the products that are being sold or purchased, the price, the units and sales, how many units of the product is sold, and how much was the sales. That is just like price times unit gives you sales. And if there's any kind of promotion involved, sometimes they offer BOGO, buy one, get one kind of stamped on the receipt, but there's also other information. But so this is really very, very, very important data that you should know. Whenever people talk about transaction data or invoice data, they are talking about this most granular, but at the same time also most empowering piece of information in any kind of transaction or in any kind of business firm. Second, let's talk about this, what they call cross-sectional data. Cross-sectional data is another form of transaction data. It's collected in a single time period, samples different subjects at each point in time, and it could be on products, individual firms, and in this particular case, ordering is not important. Time is not really a component. This is really just like you go into a class and measure the height of the students, or you go in a store and interview the customers and record whatever information that you are getting. So it is done at one point of time, and it is like it's like an information that will provide some kinds of actionable insight from specific groups of people. Could be cars, could be customers, could be country, could be whatever, could be specific community, could be any kinds of manufacturing plant and so on. So this kind of data is called cross-sectional, very simple, very straightforward, and it is being done at one point of time. The other structured data is time series data. I would like you to know about this very, very important data, and it is collected over a regular, fixed, and equally spaced time interval. And chronologically sequenced, time is an important component in time series data, like product sales, population density, stock prices, interest rates, weather, and so on are time series data. The time from one measurement to the other could be measured in weeks, in months, in quarters, in hours, could be. It's possible to arrange it, but the distinct and the most important component or feature of time series is that it is regular and fixed, and they are equally spaced. Like for instance, a table that you see on the left is a purchase of milk happened every week in January, February, March, and on the right side is a temperature of a small town like one good town, I call it. Could be Columbus, could be any town. And the temperature measured every month, if sequenced, it could be a time series data. Now you might probably ask, well, January in terms of length may not be the same as February and so on. So when you are dealing with that kind of stuff, like for instance, weeks within a month are not always equal length, right? Some months are 28 February, some months are 31. So if you have to really just like divide them into 7 days, weeks and stuff, it may not be. So there is some kind of adjustment factor. So before you do any kind of analysis on time series data, you do this adjustment, making sure that the time span is equal. So this is critically important for forecasting. Most of the time we use time series data for forecasting purpose. And we'll actually cover some forecasting concepts and analysis at subsequent chapter or discussion in this class. So we saw transaction data, we saw cross-sectional data, we saw time series data, and the other one is panel data. Panel data is a very, very important concept in analytics. It combines cross-sectional and time series features. Time element is there, and also multiple entities are there. So when you are tracking same sample at a different point in time, useful for measuring trends and changes, say the shopping pattern of specific number of customers, not a single customers. Whenever you're talking about panel data, you're talking about large number or more than one number of people or entities. So this kind of data is used in marketing, economics, financial studies, sometimes called longitudinal data. You would probably encounter these kinds of expression depending upon the expertise of the writer. Panel data can be called panel data by marketers. Some economists might say longitudinal data, and so on. So it is a repeated measure done multiple times. The timing don't have to be equally spaced like time series, but definitely it's a repeated measurement on groups of entities, and sequence is very important. And at the same time also the entities should not really be just one, should be really just like more than one. So we got structured data, we got structured data, has got panel data, we got cross-sectional data, we got time series data, we got invoice data or transaction data. Whenever we're talking about structured data, these are really the most important components that we need to understand. Unstructured data are numerous, and they come in different shapes and forms. And this includes emails, GPs, from blogs, from forums, from a spreadsheet, from videos, from YouTube, audio files, and so on. So there are different ways. Oftentimes you get the unstructured data, the intent of the purpose, the intent of the analysis. Once you get that, you convert the information into some kind of structured data, and you can apply the classic analytics technique. So they are kind of interrelated in terms of like, okay, well, I got this data, I have to count them, right? If I have to deal with text data, I have to count the number of texts. I have to really just like look at the trajectories and so on. So the kind of analysis that is being employed is very diverse, of course, and we'll see there are new emerging techniques in machine learning, but unstructured data is huge, and it is really the overwhelming amount that we encounter, and it is very empowering at the same time also challenging to analyze and get the information out of it. So unstructured data is just like indicated in the earlier slides, video files, audio files, emails, sensors data, not a good fit for a mainstream relational database. Like we said earlier, the storage is a different style, and it's very big and diverse. Most of the data are not processed. As I said earlier, we have only leverage at this point of time about 2%, 3% of the total amounts of unstructured data that we are getting on a daily basis. So there are, like I said, there are lots of analytic technique, natural language processing, machine learning, neural nets, and a bunch of other stuff can also be employed on the unstructured data. The goal is to convert the unstructured into structured and do various kinds of analysis to really extract some actionable insight. There's also other way that we can classify data, which is the traditional and the big data. And this is a no-brainer. Traditional is volumes in gigabytes. The big data is volume in much gigabytes. We have got terabytes of data. Sometimes I work on a data that constitutes like about 1 billion records, rows, and several hundred columns. And it's also not uncommon in the kind of work that I do to deal with about 5 billion kind of rows of data. And when you are encountering this kind of data, the space processing units are kind of a challenge, but there are technologies that would circumvent all that and make our life much easier. So big data, whenever you're talking about big data, it really can be huge and huge and huge. Like when I came out from college, my thinking process was kind of what's big data? I think the first interview I got was, how big data have you handled in the past? I told them, well, when I was working on my PhD, the university atmosphere, oftentimes 10,000 lines of data is considered big. I told them, and they just laughing at me. Well, you'll learn that even 500,000 or a million line of data is nothing. It's just like a small piece. So traditional data has got velocity per day per hour. The big data velocity is very rapid, and the traditional data variety is limited. The other one, as you have seen already, is very diverse, and storage is centralized. The other one is distributed, simply because when you have got big sites, you have to make sure that the data that you acquire is not really put in one place, just like distributed, and that is really good for quick updating and quick accessing. And the relational database, the Microsoft SQL, Oracle, and so on. This one have got Hadoop system and NoSQL and so on. So they are quite different, and this classification is oftentimes understood to reflect what we encounter in terms of like data analytics and machine learning. They are kind of similar to structured and unstructured, but still there's some kind of overlap. Okay, we now proceed into the 4 V's of data. First, before we proceed go there, I would like you to really just like look at this particular table. And oftentimes when I'm extracting information from somewhere, I show the reference or the source at the bottom. Unless there's something is really just like so obvious, you'll find it in every textbook, and there's no need to really just like put the resources there. So oftentimes we are measuring data in bits and bytes, and as you know, kilobytes is 1000 bytes. A byte is an information where we can put 8 bits of information, and the number can go to megabytes, gigabytes. These are a kind of measurements that we are most accustomed, but as we go into terabyte, petabytes, hexabyte, and so on, the number can be really just like very overwhelming. So whenever we are talking about this big data, we are talking about in terabytes, petabytes, and so on. So it will help us really appreciate how big a data can get. And whenever we are talking about size, measurement also is an important component. It's nice to really know this one here and be appreciative of what is at stake, especially when we are dealing with these large amounts of data. The 4 V's of data are: the first is the volume. So in terms of volume, 90% of today's data was acquired in the last 2 years. 90% of the entire data in human history is acquired in the most recent 2 years. And this has been true consistently last year, before last year, and so on. So most of the data that we have is always, especially in the most recent years, was acquired in the most recent 2 years, and this is going to continue for in the future, and we'll see how the trajectory change. But our understanding is that the data volume is huge, and most of them, as we have seen earlier, is unstructured data. Velocity or internet traffic is huge, and I think this data is compiled a little bit earlier. I think it's about few years older, but what held us true last time also holds true this time, although the magnitude might be changed. Of course, change definitely. Variety is unstructured data, accounts for 9%, just like indicated earlier, and cost of poor data quality is 3.1 billion data. Well, that one we'll talk about into veracity. So these four things are very critical, and the next one is volume. Of course, the data volume that we are acquiring is in zettabytes. Is staggering. It grows almost exponentially, and we need to be really very creative. We need really to leverage technology to store it, to process it, to analyze it, to clean it up. So there's quite lots of work that need to be done with this kind of data. And the other piece is velocity. Velocity is just like how fast these data are coming, and the appetite for faster and bigger data is on the rise, as shown in here. 1 terabyte of trade information happening every session. And when you are also looking at by 2016, that was a projected one, almost 19 billion network connections that are happening. Some of the numbers are mind-boggling. What is this all about? But think about it. This is really talking about globally, and it won't really be a really big surprise if the number is correspondingly big as well. So definitely velocity, we are acquiring data at a very fast rate, and compared to like several years ago, we are now really getting things live in so many cases very quick and very fast, and large amounts of data is coming in. Of course, variety, not only contents but also sources are also diverse. They come from social media, from shopping activities, and so on. And this kind of information, of course, is unstructured data, and it accounts for the lion's share of the volume that we are receiving. And with it, like I said earlier, comes challenge, and of course, if the right tool are used, the prospect of really empowering us. I think the journey has already been launched, and so many headways are being done, and definitely I am one of those people who believes that the future is very bright, simply because technology and big data is with us. Veracity, with these kinds of velocity, with these kinds of volume, comes also, okay, like quality control issue, the trustworthiness issue, whether the data is fake or whether the data is influenced by this and that. This is really something that comes with the territory, right? Whenever you are already having this wealth of information, everything is not hunky-dory. There could be some challenges, and these are the kind of challenges that we need to stand up and definitely tackle or manage. Excuse me. So just to appreciate how data is coming, I put some slides just for your consumption. The world is increasingly becoming digital, and as you can see in here, 7.7 billion people are urbanized in the world. 5.1 billion people are unique mobile users. It is mind-boggling. Virtually 75%, 67%, almost 70% of the world population is using mobile devices of one form or the other. The internet use is close to 60%, and this number would definitely grow to become 70% or more as time goes by. So we are increasingly becoming very digital, and this is really a good thing. I'm one of the believers that the more we are connected, the more our humanity is empowered, and the more we harness energy resources, and of course the more we manage all of the climate and issues that really matter or dear to all of us. Active users of social platforms have large membership, and look at this one here. Actually, it's just like huge. When you are looking at from the top down is the list of the social platform active users is just from Facebook's all the way down to the most not visible, just like huge, and in terms of millions also. I can enlarge this one and see the numbers, but definitely the social media users is expanding, and the numbers is of course mind-boggling. The data usage is also increasing. Monthly mobile data used by the average smartphone worldwide is 7 gigabytes. Every person is using 7 gigabytes of data in the world. Of course, there is tremendous variation from developed nation to developing countries and so on, but on the average, people are increasingly being data consumers, in that amount, as we see from this trajectory, will be increasing. Data usage is also increasing. This is actually pretty much similar to the previous slide, except that in this particular case they are showing it year by year, and showing also in the circle, in the white circles, the percentage change from 1 year, from 2014 to the next subsequent years as well. So social media users is increasing, and it may not really increasing this way indefinitely. At one point of time it will plateau. However, it will just show you that such kinds of trajectory is where we are in right now. The other piece associated with this, the 4 V's, is that the resources that are being allocated on data and the dire need for data scientists. As you can see in here, 47.5 billion annual spending on big data. The average expenditure on data-related initiatives or business is 7.4 million. Of course, there is huge diversity, big firms, medium firms, small firms, but that's just the average. It's huge amount of money is being spent on data, acquisition of data. And they are also measuring that the good usage of data enhance return on investment, profit, operating margin, and so on. And these are really quantified. And if something is going to really empowering you, it's gonna bring you more return for investment, you'll invest more on it, right? Simply because it is a proven tactic, and it is a tool to really just like help you reach your destination. And as time goes by also, more data is being produced, and this is not really any different than what we have already discussed. But overall, the trajectory on investment, the trajectory on big data, on digital data, and so on is really increasing. And there is correspondingly a demand for data scientists. All this data, all this information has to be synthesized, has to be processed, and for people like you, like me, this is great news, and this is something that we have to be very happy about. Well, we saw some features of data and where we are right now historically, and next let's talk about data measurement. These are very important concepts. Whenever you're talking about data, you need to know about data measurements. So basically, when we are talking about data, most of the time this one is about structured data. Let's just focus about structured data, because the unstructured data is for the most part quite complex, quite big, and so many things require a new paradigm. Let's just focus on the structure kind of data and how we classify. The first one is quantitative data, and second one is qualitative data. The quantitative data are measurable or countable. How many, how much, how often, how far. You can ask these questions and you can get the answer for them. And this includes sales, temperature, height, weight, counters, income, and so on. These are all quantifiables. So things are counted and there is number attached to them. The qualitative ones are categorical or nominal. What they call them nominal. They are basically interchangeable names. And this include names, symbols, codes, colors, gender, and so on. So both kinds of data can be gathered from the same data unit and perhaps also from a different sources. But they are very critical components in data analytics, as we will see later. So how do you classify them? So you can classify into quantitative and qualitative data. Right? We have already described what quantitative and qualitative is. And within the quantitative, you have got discrete and continuous. The discrete ones are, they don't have any fraction or ratio, like when you are counting people, when you are counting cars, when you are counting eggs. There's not really any kind of fraction, right? It's just like one discrete number. The continuous ones have fractions, and these include like weight, temperature, and so on. If you are measuring weight, there's always weight, 110.5 pound, and so on. Height, unit price, for instance. Unit sometimes can also be measured that way. And the continuous one can be divided into ratio. 0 is absolute, height, weight, and so on. And the interval ones, 0 is arbitrary. Sometimes you don't have any kind of zeros, like temperature or date. These are the continuous variables, but they are kind of based on interval. The qualitative ones, there is a binomial, 2 mutually exclusive ones, like yes, no, good, bad, up, down, that kind of stuff. The nominal ones, they are unordered, color, taste, geography, and there is also another qualitative called ordinal, where the entities are ordered, like survey scales, rank of generals, or military, like the 4-star generals, 3-star, 2-star, and so on. So the easiest way to look at them is, okay, what are the quantitative measurements? These are basically what we have seen. There's discrete ones, count of customers. There's continuous ratio, like the one indicated in the middle. And this includes like count, weight, length, and so on. The continuous intervals are the last one. These are the temperature and ACT score, dates. These are like the continuous intervals. So whenever we're talking about quantitative measurements, these three are very critical. You later see that knowledge on this one is very, very critical. It looks like, okay, well, this is like, I know about this one here when I was 8th grade or 9th grade. But trust me, even if you are working on your PhD, you got to really just like quickly identify and select the right kind of analysis based on the type of data that you are using. Of course, the qualitative ones also, binomials, nominals ones are the ones that are not ranked or ordered. It's like, for instance, region, you're talking about east, west, north, south, and so on. It's not really just like have any kind of order. Excuse me. I have some allergy, looks like. And the ordinal, okay, like when somebody is racing marathon, the first, second, third, these are the kind of data, what we call them. They are ranked, ordered, and are called qualitative and ordinal. So these are the way how we are really measuring data into qualitative, quantitative, and within each of these two, there are also some subgroupings as well. So the other thing that we should know about this kind of data is that, okay, How do we compute them? If some data is discrete and ratio, you can't do anything virtually. You can order them from top to down, bottom. You can count. I'm talking about the one on the right side. You can count. You can compute mode, median, mean, range, subtract, multiply them. There's no any kind of limit. Now, the moment you are going into the interval one, like this temperature or date, you can order them, you can count them, you can compute the mode, median, and so on. But when you are coming into multiplication, division, no, you cannot do that. And when you are also coming into the ordinal ones are what? Qualitative ones. These are order ones, like what we say, the race or generals and stuff. You can order, count, and you can compute mode, but when it goes to the other ones, you cannot do anything about these kinds of data. So there are limitations, and same time also there are things that you can do and you cannot do. The binomial also is shown in here. Ordering, you cannot order it because it's 1 and 0. And counting, you can do, and the mode, you can compute the mode. And the other statistics and addition, multiplication, you cannot do this one here. So it's always nice to be mindful of what you can do with this kind of qualitative, quantitative data. They have got their own do's and don'ts, and it comes with what they are. Let's just talk about data distribution. This is an important concept. It's very important because we're going to be using in lots of the predictive modeling analysis, because lots of the analytic approaches that we are using require some sort of assumptions. Let's not dwell on that one. Let's just talk about why data distribution. Because it provides invaluable information to describe something about data, about trends and trajectory. If you know about data distribution, you will be able, just by looking at it, okay, what is the trajectory of this data? It has been in the past, and where it's heading, where it's right now. And missing pointers and outliers, you'll be able to see from the data, especially if you visualize them. If you are using some kind of visualization, we'll be looking at that one eventually in one of our class. Associations, benchmarks, baselines, you can look at the distribution and be able to really just like find out, okay, what are these kinds of features. And the behavior of measured targets like purchase, unique, and features, overall behavior, well, like for instance, what's the customer behavior? I'll show you. Just there's one very simple example which most likely you have seen it in the past, and shows you that by looking at the distribution, you can really tell the behavior of certain entities, customers, or merchants, or nature, climate, or whatever. What type of analysis to conduct? More than anything else, once you know data distribution, you will be able to make this critical decision of selecting what is the approach, what is the method that I can use. Certain analysis require certain types of distributions, and the most popular ones are the classic parametric statistics ones. All of them, they are very, very strict requirements. They have strict requirements in looking at the data has to be normal. It can be a costly mistake to use an analysis that is strictly requires a normal distribution with a non-normal data. That's one example. Simply because if the method, we'll check it later on, any kind of analytic method, the first thing is that, okay, my requirement to be used is that certain data distributions have to be met. If it doesn't, then you are violating the rules, and you may really just go somewhere else and select a different method. That's what it's saying. So by knowing the data distribution, we'll be able to really know what method to select. Third, understanding data distribution must be the first step before applying any machine learning, statistics modeling, any data science analytic work. And I want you to remember this very critical concept. If you are going to any kinds of meetings where some kinds of discussion is underway, you have to really ask this simple, very critical question: what is the data distribution like? and you'll be surprised the kind of answer that you are getting. And that will tell you that, okay, this is the right kind of method or not, and so on. So before, also in addition to that, before you do any kinds of analysis, machine learning, statistical modeling, you know your data distributions. Very critical. What is data distribution? It is a functional listing that shows all the possible values, intervals, and how often data occurs. That's just like what it is. It is just like the way how data points are distributed over time or over a specific scale, selected scale, and shows, okay, the contents, the magnitude, and the trajectories of the data pointers. Once data distribution is known, probability of any one particular observation in the data can be calculated in the sample space. So once the data distribution is Poisson or normal, then you can really compute the probability distribution of a specific point, because as we can see later, each distribution type has got its own parameters, and those are used to compute the points that you are interested in within the framework of the data distribution. There is PDF. It is probability density function. Every distribution has got some kinds of PDF, and typically when you have categorical data distribution, categorical data, like qualitative data, distribution don't really matter that much, as long as you know the percentage, because like if the data is yes and no, you want to know the percentage of yes, percentage of no. If your data is about like color, green, yellow, red, you want to really know just the percentage distribution, and you'll be fine. So this is where you first realize now, okay, the type of data also impacts the kind of distribution I must know, right? So you only need data distribution for quantitative data. Numerical data is organized, often ordered from smallest to largest, and that is oftentimes what we call some sort of distribution. Most important first step, like this is already described before, and every model has its own assumptions, because those assumptions are the basis upon which all the algorithms are computed or developed. And there are hundreds of data distribution. Types. The most familiar ones are Bernoulli, normal, Poisson. We'll talk about them, and lots of them we are not really interested to know, because first of all, we know what data distribution is all about. We know that there is some kinds of parameters that are being used to describe them, and each of them can be defined in a specific ways. And as long as we know the most important ones, or the kinds that we use on a regular basis, I think that will suffice. Let's just look at this particular data. When you look at this data, it is the purchasing behavior of 4 customers, customer A, B, C, D. When these customers have made purchase for 11 weeks, and what they did was they went to the store and purchased whatever the amount, and this is the unit, the price they paid. I didn't really show the units. And what you see at the bottom is the total, the mean, the variance, and the standard deviation. And all of them are identical. Like the total is 76, each customer spends $76, and overall, on the average, they spend about $7. The variance among the distribution is about 7 to 8 or 9, not really a big difference. The smallest one is 7.3, the highest one is 9.1, and the standard deviation, which is the square root of the variance, is about the same across the 4 customers. Now, when you are looking at their distributions tells completely different story. The first customers is showing a steady purchase habit where the overall purchase increased over time. The second one has made a purchase in the middle of his purchasing time and things declined. You might say, okay, this customer has purchased enough, he don't really need. After that, maybe he's consuming what he has already purchased, or maybe he is hosting some kinds of social functions, some kinds of events. For that, he has to buy more. Later on, when that event is not really happening, the purchasing declined. The third customer purchased very little every time, but at the end he purchased huge amount. And you say, whoa, this guy is really just like having some kinds of event, or maybe because of price or whatever marketing reasons he has to, or personal reasons, social reasons, whatever, he has to really make that huge purchase in one day. And as is the fourth customer, where he made this continuous huge purchase, he came back and forth and into the store and made quite lots of purchase in a single day, and the other days were very sparse purchases. So by just looking at the distribution, you would be able to really tell different kinds of purchasing behavior, different kinds of patterns, and this actually is the essence of distribution. Before you go into computing the summary statistics or whatever kinds of models that you like to develop to extract parameters, just look at the distribution and learn from the distribution first. You would be really serving yourself and your team and your company a great deal if you always do a diligent work in characterizing your data through its distribution, because the distribution tells everything, and it is the most empowering first step in the entire scheme of data analytics projects and activities. So also from the distribution you can look at if there is like an outlier. The second graph shows you that things were going nice, the same kinds of rate of purchase, and all of a sudden you have got these kinds of very anomalous behavior. And the third one shows you like, okay, a steady increase and then eventually decline. So visual display, just like the earlier slide, can tell quite so many things: trajectories, missing values, outlier values, and of course anomalous behaviors, and so on. So distribution is always an important component in your work. Let's look at these four distribution. One is the Bernoulli distribution. This is important. We'll see. We'll have homework and so on. And also, when you do your projects, you have to really just like work on or understand certain distributions, and most of them are the ones that are indicated over here. Excuse me. So the Bernoulli distribution is the easiest distribution of all, and event has only two possible outcomes, right? And this is the kind of stuff that you say, okay, success or failure. But it does have to be that each of them has got 50-50 kind of chance. Like, for instance, you toss a coin, you know that one, head and tail. If you toss it for large number of times, their probability will be about 50-50, right? But the Bernoulli distribution describes events that have got like two outcomes. However, the outcomes are not always 50-50. It could be like, for instance, a boxing match, right? One will be very high odds of winning, and the other one is low odds of winning. Maybe also like racing. One probably be elite runner, the other one maybe not. But when you are looking at them, there are two outcomes. Either one win, the other one lose, kind of, the other one wins. So this kind of distribution is called Bernoulli distribution, and it is expressed by two possible outcomes. I mean, of course, the yes or no, and there are plenty examples in life that can be described by Bernoulli distribution. Actually, lots of things that we are looking around: rain or no rain, sell or no sell, winning a lottery or not, or maybe getting some kinds of event happening or not, meeting a friend or not. Those kinds of things can be expressed by the Bernoulli distribution. The other one, the most popular one, which I'm sure you might be familiar with, is the normal distribution. It's called the bell curve, or the Gaussian distribution, named after the first guy who computed the PDF and introduced it to the world, Carl Friedrich Gauss. And interestingly, lots of these key discoveries happened in the 1980s and in the 18th century or in the 17th century. And yeah, that is a very mind-boggling. If you look at the critical algorithms in statistics, mathematics, and so on, physics even, have been discovered quite a long time ago. Describes most events, phenomena. So human height, weight, IQ score, and stuff always follow the shape of curves. And if you have like a class, analytic class, or anything class, oftentimes it shapes, follows some kind of normal distribution curve defined by the mean and standard deviation, and the PDF is shown at the bottom. That is just like how you derive the graphs. We are not interested in really going through there and compute the values, but what we can learn from there is the mean. For normal distribution, the mean, the median, and the mode are always the same. The total area under the curve is always 1. And for the standard normal distribution, this is what they call standard normal distribution. The center, the mean is 0, and the standard deviation is 1. So any kind of statistical models, especially parametric statistical models, require the data to have a normal distribution. We'll discuss about that when we are reaching into the predictive model development section of this class. And you might also know about this, the 68, 95, 99 rule, and this one is for a large sample of data that assume normal distribution. 68% of the population is within one standard deviation, and 95% of the distribution are within 2 standard deviation, and so on. So this is just like a way how you can tell things are dispersed in a population. And if you are really collecting data of any sort, and if the sample is large, it is not unreasonable to assume that your 68% of the population is within one standard deviation. The moment your data is not normally distributed, then this kind of assumption do not hold to be true. So always remember this one. Your size also matters when you are really talking about specific distributions and whether you are going to implement certain rules that comes out of it. The other one is a binomial distribution. This is basically a kind of distribution. It's used for events with 2 outcomes, success or failure. The typical example is like tossing a coin, and each event has got equal chance of success or failure, which is really quite different from the Bernoulli distribution. And the parameter for this one is the mean and the variance, and either success. So the NNP. So this one is like you have got 2 graphs, and the moment you are changing the variance, things, the mean, things shift from the left to the right, and so on. So the binomial distribution is really quite common, and there's quite lots of overlap and similarities. We don't really need to go to that one and make it very much about probability. There is a section that will talk about like probability, and when we are reaching there, we can be explaining some of the deep concepts of probability. But basically, this is just like to have a high level of appreciation. What data do we have, and how do we really just like select one versus the other? What do they look like, and so on. Otherwise, we can spend the whole semester discussing each of the hundreds of probability distribution types. As long as we know, okay, there are certain things that we need to really understand, and as long as also we know, okay, these are the reasons that we are using this distribution versus this, that I think is enough, at least for this class. Then the other one is the Poisson distribution, and this is applicable in situation where events occur at random points of time and space. The Poisson distribution actually describes quite so many things in our life. Events are independent. Probability of success over a short interval must equal the probability of success over a longer interval. That means no event is going to influence, no drastic or sudden event is going to be coming and change, upset things. You know, like COVID comes and all things were upside down. Not like that one. Like, for instance, emergency calls or customer calls for any kind of services. Or unit of product sold in a store, and so on, can be explained by the Poisson distribution, and depending upon the variance and the variability of the data, the Poisson distribution can also have some kind of similarity to the normal distribution as well. It is the parameter for this particular distribution is the mean. The variance also is an important component in this one as well. So in terms of distribution, the Bernoulli, the binomial, the normal, and the Poisson are typical examples, and this is really something that we should really know about it. So there are lots of other kinds of distributions, the Kane distributions, the Borel, the gamma distributions, and so on. We don't really need to go into this one here and spend our time understanding them. So in general, today we learned about data and data mining, the why aspect of it, data types, the 4 V's of data, data measurements, and last but not least, we learned data distribution, and this will be followed by some Python lectures in the part 2 of the lecture 2, and I will see you in there. And if you have any questions or any kinds of points, please reach me out, and I'll be very glad. You can email me, or you can use the office hours as described in the syllabus. Thank you so much for your attention, and look forward to see you next time. Take care.